Now look, we are at the top of your notes. It says Unit 2 notes. This is Chapter 4 is just part of Unit 2, but it's the big part. Okay, so this is going to be. We're going to just do standalone. You know, when we had our first test, that was really 3 chapters, right? It was a lot of review, but it was really 3 chapters. Shh. This is going to be a standalone. And I think I told y'all this last week. I can't remember. Last week was kind of crazy. I'm going to break this down into 2 tests. Okay? We're going to have one. You'll see as we go through some things, you're going to have one up through a certain point, and the second one is going to be just acid, base, and redox, because that stuff's going to be new for you. Okay? So I didn't want to throw that into this test. So 2 tests for this. But that doesn't mean that it's going to be 3 weeks in between each test. We still have to move, okay? There is some vocabulary that goes with this, and some of this stuff should be a piece of cake. You know this stuff. This stuff goes way back to 8th grade physical science, okay? A solution. What kind of a mixture is a solution? This is another name for what kind of mixture? Very good. This is a homogeneous mixture. It means it's the same throughout, right? Now, on the last test, when you see an acid of any kind, if it's part of a reaction, acids are, if they are aqueous, which they all are, it is a solution. It is a homogeneous mixture, okay? Always. And a lot of us missed that on the last test. All right, the solute. Now this was, I think, a warm-up last week. This is what is being dissolved. Now, you can say solute, you can say solute, I don't care, okay? The solvent, that's what's doing the dissolving. And this is not very scientific terminology I'm using, but I want to be sure you understand it. What is doing the dissolving? And it's usually what? Water. Soluble. What does soluble mean? It will dissolve, right? It dissolves in water. So this, it means it will dissolve. And here's where we run into a problem. And I forget about this sometimes. But you remember last year when we were doing our reactions and we would have a compound, let's say it's compound XY, and beside it we would put like a solid or an L or an AQ. All right, S for solid does not mean soluble. And sometimes we forget that, okay? If it's a solid, then it means it's what? Insoluble, okay? If we had something that turned solid and it turned into these little flakes that fell down to the bottom of the liquid, and we've seen that happen before, and we'll see some more this week. That solid that formed is insoluble, okay? That means it will not dissolve.
So if you have like little pieces left over, that means it's insoluble?
Right, and that is the PPT. What's that? The precipitate. Very good.
I wish I do this good on my next test.
See what I mean about some of this stuff is going to be review. It's going to pull some things back that you learned last year. Hmm? You got one last week.
Oh, I did?
Uh-huh.
I don't know if I had it.
All right, just try to find it. If not, I'll see if I can locate one. It should be in your notebook. All right. Shh. Wow. Having some trouble. I just told y'all we got several things we got to get through. All right, what does aqueous mean? Yes, in a way. It means it has been dissolved in water, right? If I have that acid I was just talking about, and I know it's a solution, of course it's aqueous. It's been dissolved in water. Okay, it's been diluted. All right, water is the solvent if it's an aqueous solution. Water is what we call the universal solvent. Now, I don't know that we did this last year, but we're going to do some this year. Water has what we call a bent shape. Bent.
Like the molecules?
The molecule is bent. Y'all, when you, let's say this first, and then I'll tell you what I mean over here. The bond between the oxygen and the hydrogens, those are the covalent bonds. We know that, right? A water molecule is covalently bonded together, because these are all nonmetals. And water is a good solvent because what kind of molecule is water? What kind of covalent molecule? Starts with a P.
Oh, no.
Like the big white bear up north.
Oh,
It's a polar molecule. Y'all remember that?
I remember that.
All right, we might not have talked much about it, but it is what we call a polar molecule, and we will talk a good bit about that here shortly. But what that means, if it's polar, it has an uneven, and we did talk about, y'all remember we talked about electronegativity values?
Yeah.
And we subtracted them, and if you fall into a certain point on the little scale, then you're polar covalent or nonpolar covalent or ionic. Okay. This is an uneven distribution of electrons, okay? And it's going to be what we call not symmetrical. Of course it's not, because it's bent. All right. What makes up a water molecule? 2 H's and 1 O, right? There's my O. And here's my H's. Okay? And we're going to talk about, when we do what we call Vesper structures, which we'll get to, we're going to talk about why molecules take on these different geometric shapes. And some of us, like me, that aren't spatial people, I'm more logical, give me a formula and let me plug some things in. I'm not very spatial. But we have to keep in mind that this is not happening in two-dimensional space, right? This is more of a 3D type thing going on here. But what happens is, do y'all remember which of those two elements it has a stronger or higher electronegativity? Oxygen. Hydrogen's really small, okay? Oxygen is higher, it's a little bit stronger. So it's pulling, and what's it pulling? What is it pulling? What is on the outside of these that causes bonding? Electrons. So oxygen is pulling these electrons, okay? And hydrogen's only got one out there, right? It's pulling that one little electron towards it. So if you're what charge does an electron have? Negative. So if you're pulling electrons to you, what kind of slight little charge do you think you're going to take on? Pulling negatives. And this is just like a little sigma. It looks like a little S, and I like to think of it as an S. It's a lowercase delta. It is a lowercase. Look, to me, it's a little fancy S. And let me tell you why. Because I can think of that S as slightly, right? S for slightly. Slightly negative. Okay, but this is the symbol that you'll see. See, I'm bringing to the calculus. No, I'm not either. Trust me. I still have nightmares about that little summation type symbol thing. All right, right here. If you're pulling this negative away from you, what charge will you become? Positive. So slightly positive. Okay? Now, this property right here is why we are able to have life. Without it, we would not have. I mean, there's so many things that could go wrong without this little. This is a miracle right here. This right here is a total miracle, seriously. Because that slight negative of that oxygen, if I've got another water molecule here and this hydrogen is slightly positive, what's going to happen between a negative and a positive? They're going to, two opposite charges attract. So the water molecules kind of want to come together and cause surface tension, right? And cause cohesion and adhesion. And it causes, what happens to ice, water ice now? When it freezes, is ice more dense or less dense than water?
Less dense.
It's less. Now, normally a solid is going to sink in the liquid. But because water has this unique property, this is actually going to push apart a little bit, and make ice float. What would happen if it sunk and all the oceans and the rivers and stuff froze from the bottom up?
Is that why glaciers
We would
float?
have, everything would die.
Is that why they
Okay.
float?
Huh?
Is that why glaciers float?
Yes. This right here is why why that we're able to maintain life, okay? All right.
Hey, so does that do that in our body?
What you mean?
We drink water, does that do that in our body?
Was it, does it what? No, because you're thinking about, it's gonna go by molecule into your cells and stuff, right? Not in globs. All right, hydration, what does it mean to hydrate?
Add water.
Okay, add water. It occurs when salts dissolve in water. And water has the ability to dissolve most ionic salts. That's why we call it the what? What do we call water?
Salt.
Universal solvent. Okay. It can also dissolve some non-ionic, non-ionic basically is covalent, right? It can dissolve some if they have polar bonds. Will it dissolve oil? No, because oil is non-polar, okay? Only if they have polar bonds. It's pretty tough. All right, solvation with an O. Solvation. It's the physical act of dissolving something. That just makes sense. The only reason I put that there, not that y'all couldn't have figured that out, but I didn't want you to see that word and think it said salvation. Okay? Solvation means dissolving something. It does look like it. All right, so we're going to pretend here, and y'all know not to make fun of my drawings because you know that hurts my feelings, okay? So if you listen to me while I'm drawing this, then you can make yours look better. I'm sure you can. But let's say down here at the bottom, I've got this ionic compound, hush. It's salt. We're pretending. I've got some sodium ions, and I've got some chlorine, don't I? Okay, sodium, chlorine. That's what this is made up of. Now, if I throw some water in here, or if I throw it into some water, and I've got these negatives and positives, okay? Of course, there's more than one water molecule. What do you think is going to happen to, let me put that positive closer to my H over here. All right, y'all kind of see what I'm going for here? I've got my salt down here, my sodium chloride, and I've got it in some water. Is this to scale? No. We're just trying to get an idea here. What's going to happen with these positive sodiums and these negative chloride?
With the positive attracted to the ice.
Yeah, the salt launch.
This sodium is going to be attracted here, these chlorines. So what's going to start happening to this salt? It's going to start splitting up, right? It's going to dissolve. That is what's happening. That is how things dissolve in water, is because, once again, this miracle up here that we just talked about with these slightly charged ends causes this to pull apart and dissolve. So y'all you heard what I was saying, and your drawing, I'm sure, can end up looking a little better than mine. Just be sure you see that it's going to start pulling apart. So I'm going to have like these negative chlorines attracted here, and I'm going to have some positive sodiums attracted, right, as it splits apart.
So then they become a part of the water? Is that what we see?
Yeah. As far as sodium chloride goes, yeah, kind of. Huh? Okay. Okay.
Write him up.
I love you anyway. Okay. traditionally. Y'all don't laugh at them. You're encouraging them. All right, we good? I didn't want to move my beautiful drawing until I'm sure everybody was okay. All right. All right. How much of a substance, we're talking about solubility, how much of it will dissolve in a given amount of water? We're usually talking about grams per 100 milliliters of water. It varies. But if they do dissolve, then the ions are separated, which we were just talking about, and can move around. Now, y'all have heard of electrolytes. You hear that on commercials all the time, right? What kind of drink do we hear about all the time with these electrolytes? Gatorade and Powerade. Gatorade. The first one was the Gatorade, okay? Now, when you drink Gatorade, if you drink Gatorade, you'll notice it's got a slightly salty flavor to it, right? It does. It's got just slightly, which is really good marketing for those folks down at Florida that came up with this, because it does have that salt that because you lose that salt when you sweat. So that's supposed to replace that, but salt makes you even more thirsty, so you drink more. So that's great marketing, right? Because you drink more Gatorade, supposedly. All right, so strong electrolytes. These are substances that completely ionize. What I was just showing you in that drawing was ionization, ionizing, because I was taking the compound and splitting it into the ions as it dissolved. Completely ionize when dissolved in water. We'll put in water, even though that's kind of understood. When dissolved in water. All right? They conduct current effectively. Conduct current. Gatorade conducts electricity.
Can we test that?
Some of y'all have done that before. I don't know if y'all, but I've had several students do that for like science fair projects. All right, here's what we mean by an ionic salt. It's basically an ionic compound. Right? Sodium chloride, potassium iodide, metal, non-metal, positive, negative. All right, this is what I wanted to be sure we got to today, and we'll get a little farther than this, but I want you to go ahead and get the strong acids and the strong bases because they have to be memorized. There's no way around it, but I'm going to try my best to give you a good way to memorize. Once you have the strong, because we're going to come up to some different little reactions and some labs and some titrations where you need to know, is this a strong acid and a strong base? Is it a strong acid and a weak base? What is going on here so that you can make a prediction? Okay? Shh. Shh. All right. Here are, and I'm going to list them in the order that I give this little mnemonic device here. I'm going to put some acids here that have to be memorized. And I'm trying to make them look nice and neat, but you know I have a hard time with that too.
Is it like a wrinkle hop? Is it just wrinkle hop with the H in front?
Well, your three that without oxygen are Brinkelhoffs, right? Do you have a question? Are you stretching? Okay. All right, now, one thing you need to know, if they completely dissolve, then that means they're what we call strong. Strong and completely dissolve is the same thing here in chemistry. A strong acid completely dissolved. Strength, we need to understand this though. The strength of an acid has nothing to do with pH, okay, or how dangerous it is. The strength of an acid, the most dangerous acid of all is not even on here. Hydrofluoric acid is the most dangerous acid there is.
Yeah.
Oh, really?
If you put acid in something, it's slow to dissolve, you should add hydrofluoric acid.
Well, I'm glad you learned that on Mythbusters.
Dissolve the pH like
Oh, yeah. All right, so remember now, and I put that on there. Strength has nothing to do with pH or danger level. It has to do with whether or not it completely dissolves. All right, now, here is our little mnemonic device, and I put it down here, but I'm going to kind of list some things across the bottom so we can name it with the sentence. Here's the sentence. Imagine a perfectly clear, breezy summer night. Now, this might help some of you. It might not, okay? But if you can remember the sentence, imagine hydroiodic acid, right? Not idiotic, hydroiodic acid. Imagine, iodic, okay? Perfectly. What is ClO4? So this would be perchloric acid. So perfectly perchloric. Clear. Chloric, hydrochloric. Breezy.
Hey, Chris Breeze.
What's BR? Right, so this would be hydrobromic. And I'm just, y'all, I'm not erasing it because it's wrong. I'm just scooting it back over a little bit because I'm getting kind of far over. Put hydrochloric. All right, and then we have hydrobromic. All right, and then we have summer, sulfuric. And then night, nitric. So how many are there? 1, 2, 3, 4, 5. Okay, making sure I had 6. Scared myself for a second. And here's your sentence. If it helps you, good. If not, just start memorizing. Okay? All right, so if it's an acid like hydrofluoric that's within a reaction, you know automatically it's a weak acid. If it's not one, every other acid is considered weak. Okay? That's why we have, if we can memorize these 6, then we know all the rest of them are weak. Okay? It's a lot easier to memorize these 6 than all the rest of them. All right, same thing with strong bases. All right, react completely with water to give hydroxide ions. These are all the group 1 hydroxides. What's group 1? The alkali metals like sodium. y'all know this. I moved my thing. I keep turning that way, but you know, all the group 1. So group 1 are things like, if it's the group 1 hydroxides, sodium hydroxide. Okay. Lithium hydroxide, potassium hydroxide, those are group 1 hydroxides. And these hydroxides, the cabassers. Look, cabasser. Okay? So, to help memorize the strong bases, they're all the group 1 hydroxides and cabasser. Calcium, barium, strontium. Every other kind of base is weak. Okay? So if I have we have a little ticket out the door one day coming up soon that asks you to tell with me, I list some acids and some bases, and you have to tell me if they're strong or weak. Not today, but you can do that, okay? Or you can start studying so you can do that. It's not time to go? All right, so those are strong electrolytes. What does weak mean? Exhibit a small degree of ionization, but they don't completely ionize. They don't completely dissolve. Conduct a small current. No, now, when we talk acid-base, we don't have precipitate, and we're gonna get there, hang on, okay? All right, weak acids dissociate to a slight extent and give, what's this right here? Hydrogen ion, right? Okay, in solution. What is a hydrogen ion really?
Cat ion.
It is, but how did it become positive? It lost, and it only has one, right? It only has one proton. Does it have any neutrons? No. So all a hydrogen ion is a proton. That's it, okay? All right, so you get these protons in solution, hydrogen ions. And this, remember, is any acid that is not strong, that is not one of those six. And then the weak bases react only slightly with water to give hydroxide ions, and it's any base that's not strong. That's written in there for you. So if it's not on our list to memorize, remember, it's considered weak. Mm-hmm. Well, well, that's probably just because you took a lot of liquid into your stomach at one time. It makes it feel full. You're not going to stay like that, but you can go for a little while. And usually when you chug them like that, it's because you're hot and thirsty, and that's part of you not feeling really hungry either. Now really, some of y'all, now look here, and I told you this, some of y'all, I see you out there running, and it's 140 degrees outside, and you're out there running and running and running, and that's in the shade. Okay, it's 140. And you need to replace some of the things you're losing. But everybody doesn't need to be drinking Gatorade or Powerade. It's just not good for you. Okay? That's right, because there's so much salt in it. And your body hadn't lost the salt that you're trying to replace. It can actually, as Caitlin was just saying, it can dehydrate you because you're not out there running or sweating a lot and losing the salt and needing to replace it, right? If you're just sitting around drinking it, then you're adding salt to your body that your body didn't lose and doesn't need. Shh. Because that salt, and we're going to talk a little bit about that too. You'll do all kinds of that in biology when you take freshman biology. But you're pumping sodium into your cells instead of water, and you're adding to the salt instead of diluting it, which is bad. All right, let's do something real quick before we leave. I want just to show you, this was the warm-up, the formula for molarity, okay? That it's moles of solute per liters of solution. If you see brackets around something, that just means the concentration of. Like if I have this, that's the concentration of potassium ions in a solution. Brackets mean the concentration of. You're going to see those a lot in here. Whatever's in that. This particular one means the concentration of potassium ions. It means per liter of solution, how many potassium ions are in there, right? The concentration of it. Let's look at this little practice problem. To make a 2.7 molar solution. Now this is real life here, all my science folks, okay? When you're in lab, you need to make a solution of something. You need to know how to do that. When you're in college, they're not going to tell you. You got to know how to do it, okay? It says let's pretend we need a 2.7 molar solution in lab. We've got 50 grams of hydrochloric acid. What total volume is required? And what's the concentration of each ion? Okay? First of all, what did this capital M mean? Molarity, right? It means moles per liter. All right, so let's see. If I've got hydrochloric acid and I want to know the concentration of each ion, what ions is hydrochloric acid going to break down into? Hydrogen and chloride, right? And hydrogen ions look like that, don't they? And what do chloride ions look like? Right. So it's going to break apart because we know it's a strong acid and it's going to completely dissolve. Isn't it a strong one? Okay. How much do we have to start with? Look right here. 50.0 grams of hydrochloric acid. I want to know how many moles that is. How do I know that? How do I figure that out? These aren't, I told you they weren't going away. Right. 1 mole, I need moles, right? Moles of solute. So 1 mole of hydrochloric acid, and if I add all this up, and y'all help me because you got your periodic table and I forgot. 36.45, 46, we'll stop there. Grams. All right, so if and I think I did this, that's why I keep looking over here. What you get, 1.3 something something? I need, how many significant figures do I need?
About
3. So what do I get? Does it round up or not? 1.37 moles. Okay. So now I know my capital M molarity, and I know my moles, and can I figure out my volume? Because I know molarity, and let me write this up here. Molarity, remember, equals moles per liter. Okay? So 2.7, that's my molarity. I know 1.37 moles, and I can find my volume. I got like 1.95, but y'all check behind me. If I want to get my L by itself, I divide, right? If I multiply this side by 1.37, I'm not going to get rid of it, am I? How do I get rid of 1.37 over here? Divide it, right? Or can't y'all just cross multiply? Does that sound easier? I got 1.95. Y'all know some algebra skills. I used to talk to your math teachers.
It is already known that Mr. Moore taught us nothing.
Yes, he did. All right, so wait a minute. 1.95 liters. That is the volume required. But what's the concentration of each ion? This is the easy part. If I've got, how many moles of hydrogen ions are here? 1. How many moles of, so all that is, my concentration of hydrogen ions equals 2.7. My concentration of chloride ions equals 2.7. Because it's only one of them. Okay? It's only one. And that might be, this part might be of everything. This part might have just confused you because I just threw that in at the end. So we'll pick up there and talk through that. Let me see if the second one is similar. Yeah, kind of. So we'll go through what I mean by this last little part. Remember, brackets mean concentration. And then we'll start there tomorrow.